Today's speaker, Lovisa Hagström, is a PhD candidate at Chalmers University of Technology, Department of Computer Science. She has a master's degree in engineering physics from Chalmers, and she's been studying 1 year at the National University of Singapore. She's previously worked at Zenuity and what is now called the Zensact, and her research focus is around NLP with incorporating data, which is not text, such as grounding language models. And today, the topic is the issue with understanding language from text alone, an overview and potential solutions. So I'll hand over to you, Lovisa.
Thank you, and thank you for the introduction. I'm very happy to be invited to these seminars. So, as previously mentioned, my name is Lovisa Hagström, and this is then my presentation at the Learning Machines seminars at RISE. So, what I will be speaking about is the issue with understanding language from text alone, and I will try to provide you with an overview of this problem and also some potential solutions that have been found recently. And of course, I will also share a bit about where I stand in this context. So I have 3 goals with my talk that I thought I should share with you. And the first one is to share my knowledge on natural language processing with you. So hopefully you learn something from this about natural language processing that you maybe didn't know before. And maybe you can share knowledge with me. And of course, I also want to inform about my research in case, I don't know, we can find synergies, and also because it's fun to speak about it. And lastly, I really appreciate getting your input. So feel free to ask questions whenever, or I don't know, share experience or knowledge. And since I'm screen sharing, it's quite hard for me to see the chat. So feel free to tell me if there is someone raising their hand or having written anything in the chat.
I'll keep an eye on the chat for you, Lovisa.
Great, thank you. So just quickly, I was already introduced a bit, thank you so much for that, but I thought I could just maybe quickly go through this. So I work with natural language processing. I am a 2nd year PhD student at Chalmers. I have a Master's of Science degree in physics, and I'm also actually interested a bit in efficient machine learning. That's also something that is on the rise and quite related to natural language processing. So also I should mention that I'm a part of a WASP project group. So I'm a so-called WASP PhD student. My supervisor is Rickard Johansson. I'm also working with 2 other PhD students, Tobias Norlund and Essan Dostmohammadi. My co-supervisor is Marco Kuhlman, and our project group also has like a contact person at Recorded Future, who is Staffan Trevén. So this is sort of the context I'm working with. And if you have any questions after presentation or any ideas or anything you want to discuss, feel free to mail me on this address. Now, let's get started with natural language processing. So I thought I could start with giving some kind of overview on the field, because I'm not certain where you lie maybe. It will be quite short, but it will put you like in the context, and that might be good for the rest of my slides. So natural language processing is essentially about having machines understand our human language and understand us when we communicate about different things. And of course, this entails that natural language processing can have a lot of applications, such as spam detection for your email, or using them as chatbots or grammar checkers. Because the fact is that language is everywhere. So we use language, or at least I use language every day, either in text or spoken form, because we communicate a lot in our society, which is good, which also means that natural language processing has a very rich field to work in. And we can also see some applications of natural language processing. I have only included a few here. There are many more. So for example, one thing that maybe some of you already have seen is that there's recently been developed a quite large language model that is able to sort of generate articles based on just a title and a subtitle, and then it can come up with its own sort of context and make it seem very plausible. There are also other models. This one is a T5 and it has sort of been trained to be queried with different formats, and then it can just adapt to whatever you're asking for. So for example, you can ask it to translate something from English to German. And one application that is actually released that anyone can use, I believe, if you sort of sign up for the preview, is that GitHub has sort of created co-pilots together with, I think it's OpenAI, where you can sort of write a comment in your code, and then the model can sort of suggest what should the code be corresponding to your comment. So you get like proposals for what code to add to your script, which is quite cool. And it's a model that has been trained on quite a lot of code. So that's a bit about like a short intro to natural language processing. So now we can take maybe a more closer look at what has happened in the research field recently. And I should start by introducing language models, because that's what I'm working with predominantly, and that's, I believe, what has been mostly developed within natural language processing within the most recent years. But I'm biased in this regard, so feel free to correct me if you disagree. So essentially, the models that we use within natural language processing right now are sort of based on maybe this quote that you shall know a word by the company it keeps, which essentially means that words that occur in similar contexts probably have similar meanings. So for example, consider the word apple and the sentence, I ate an apple. You could replace the word apple with banana, and that would still make sense. I ate a banana. So maybe bananas and apples have something in common, while maybe it would make less sense to say I ate a printer. So that's sort of the assumption that is being made here. And it's also sort of expressed in the distributional hypothesis that you sort of claim that linguistic items with similar distributions have similar meanings. And this is essentially what language models are based upon. They are trained on large amounts of text to sort of model the probability of sort of what should the next word be given the previous words based on what it has seen before in the text it has been trained on. And also the most language models, or maybe even all, are based on deep learning methods. So they are deep neural networks with quite a lot of parameters, which you can see here, for example. So these are model sizes of language models, or also can refer to them as natural language processing systems, as up to year 2020. And the sort of very rapid development of large language models, or you should maybe say very capable language models, that can, for example, generate articles or code. It started, I would claim, with ELMO, which is an acronym for embeddings from language models. And what they introduced that was new to the field was deep contextualized representations, which essentially means that you create representations for words based on the company they keep in the sentence that you provided. So if you have the sentence, the cat laid on the mats, you create like a representation for the word cats, but that also depends on which words co-occurred in this sentence together with the word cats. And it proved to be very good to model word embeddings in this sense, to sort of achieve better performance with language models. And then came the generative pre-trained transformer. So here they introduced the transformer. Instead of using a so-called LSTM for modeling these sequences of words, you use an attention mechanism that enables you to sort of consider every part of the sentence while you're considering maybe even the last word in the sentence. So this was also like an introduction of something new that every model afterwards had built upon. And this model is also called GPT. So it's a predecessor to GPT-2 and GPT-3. And then we have BERT, which maybe many of you recognize because I believe it's used in quite a lot of applications, and it's very easy to just download and use. And it's an acronym for bidirectional encoder representations from transformers. So it's also this about creating deep contextualized representations. And here they just introduced that you can consider both what words were before your current word and what words are after. And then the development continues. OpenAI releases GPT-2, and at year 2020, we have the Turing natural language generation model that is very large. So you can sort of see here on the y-axis, you have the number of parameters in your model. So essentially how large your model is. And you can here see like an exponential growth in how model sizes increase over the years. And this was 2020. So now we have removed the linear scale on the y-axis, and now it's a logarithmic scale because that makes more sense due to this logarithmic development. And here we have the Turing natural language generation model again. So it was up until this we saw in the last plots. And now we have GPT-3, and we also have the Megatron Turing model. And yeah, and we can see that the models are growing bigger, and that's because they are also becoming better as they grow larger. So usually you test them on, for example, superglue, which is like a general natural language understanding benchmark test where you like test what sort of is this a probable continuation of a sentence or etc. So different sort of language properties or understanding. And you see that the models become better at this the larger you make the models and the larger training data sets you expose them to. So we can, for example, consider GPT-3. It was trained on data or text crawled from the web. I think it's based on Common Crawl. So that's 500 billion words. And you can compare that to what BERT Large, a smaller model, was trained on. And that model was trained on all of English Wikipedia at that time, plus 11,000 books, full books. And that was 3.3 billion words. So there are very large text amounts that go into these models. And that's also a very interesting developments that we're seeing. And also one just interesting comment is that one of these recent language models, it was Microsoft that developed this one, and they claim that they have created the world's largest and most powerful generative language model. So this maybe puts a bit of a title on this recent research. And I mean, it's very good that we see that we can increase performance on models in this direction. But it's also interesting to, of course, consider other directions for improving model performance. And that's what I will be speaking about. And that's why I titled this presentation, The Issue with Understanding Language from Text Alone, because what is common for all of these models I have introduced just now is that they have all been trained on text, and that's all they have ever seen. And that can cause issues, which maybe some of you already have seen some articles about, and I will move into that now. So we can illustrate this issue with maybe an example. So we have Anna, who is a human, and we have a language model, which also can be shortened to LM. And Anna maybe asks the language model, what will today's weather be like? And then she is thinking of weather forecast and different kinds of weather, and whether it could be cold or rainy or etc. The language model, on the other hand, the only context it has is sort of the text it has been trained on and the sort of probabilistic distributions of this text and what the probable continuations of different types of text are. So it will answer sunny without any reference to any actual weather forecast. And the thing here is that Anna's intent was maybe to get information about the weather because she wanted to decide on what jacket she should wear, while the language model's intent was only to generate the most probable continuation to the text or her question that it was provided with. And here is sort of one claim that has arrived in these recent years is that communicative intents are about something that is outside of language. So I know that one claim was that we don't speak because we think it's fun to speak. We speak because we want to achieve some kind of goal or task or communicate about something. And typically that lies outside of language. So this is my illustration of what the initial problem could be. And we could also see some sort of problematic examples of where this sort of is visible in language models. So for example, if you just prompt a language model with the color of a dove is, and then you ask it to fill in the blank, and you could get the answer blue. And I think most of us know that doves can maybe have many colors, but blue is maybe not the one you would expect. And there is also another example from another language model. So it was used for summarization. So here you have the result of that model being applied to a larger chunk of text, and then it was asked to sort of summarize it and shorten it. And what it did was that it introduced new things into its summarization that weren't mentioned in the original text. So it sort of involved, it wrote that this person that the text was about had gotten drugs from undercover police, and that they're also that they found weapons at his home. And this is not mentioned in the original text, but it was plausible, maybe according to the model, that it should occur here because it's a natural continuation of maybe the previous words. And this maybe raises like a thought of a parrot speaking to some extent, that you sort of say things that sort of make sense, but you don't really understand what your words mean. And you can also, for example, see one problematic example in here. I would claim that I ask this model called Bird Large essentially about the same thing. So a bear usually has, and then I have a question mark for it to fill it in, or everybody knows that a bear has, or a bear usually has. And you can see here how the model answers with different answers each time. And maybe that makes sense in some instances, depending on how you actually frame your question. But I have also seen examples where you, for example, use the word color in your sentence, and you just write the word color. I think it's in the like UK form, where you include also a U after the O in the word color. And then suddenly the model changes its prediction because you just changed that small part in the word. And that's because the model is actually modeling the probabilistic sort of most probable continuation of your words. So it doesn't sort of model what was your intent, it models just what seems more reasonable as a continuation. And this could be an issue in some instances. So there have been, as I mentioned before, there have been articles released quite recently on this. So for example, there is an article by Emily Bender and some other people, and that sort of claims this, that language models are stochastic parrots because they just stitch together words according to probabilistic information that they have learned from training on large amounts of text data, but they don't really know what these words mean. I can also, for example, provide an example. I was sort of, I don't know, writing with the GPT-2 model, and I don't remember what I wrote, but I remember I got the answer, "You're stupid." And of course, it was just a model and it doesn't matter, but it sort of used that word because that made sense in the context, but without any reference to what it actually meant. And that can maybe be dangerous in some situations. And then you also have the claim that, for example, successful linguistic communication relies on a shared experience of the world. And it's only with this shared experience that your utterances are meaningful. And there's also another side to the problem, is that, as I mentioned previously, for example, the BERT model was trained on all of English Wikipedia and 11,000 books. I don't believe I have consumed a corresponding amount of text when I learned how to speak languages. So I most likely needed a less amount than the model. So this sort of hypothesis is that the models need these large amounts of text because to acquire knowledge that seems comparable to us, because they have no other reference. And here they use the word grounding, which essentially means that you sort of connect language with corresponding concepts outside of language. You can also interpret it as sort of training a model on more than text. So the idea is sort of, if you can evolve more information from the outside, maybe the models don't need as much data, or at least text data, to train on. But then, of course, there's also the other side of this problem that I haven't spoken about yet. And I mean, you can, of course, think about whether this is actually an issue with language models. And for example, we have the article by Magnus Ahlgren and Fredrik Karlsson that sort of states that, well, we don't necessarily have to interpret language understanding as being this exact thing that Bender and Color have been speaking about. It could be something else, and that is obtainable by language models. So language models can be useful for applications that may not be in accordance with what Bender and Color speak about, but still useful. So that's worth remembering, that it all depends on how you sort of interpret what a successful performance of a language model is. But for the sake of this presentation, and because I also think it's interesting to think about this, whether you can train language models on more than text, I will sort of still assume that we have an issue with our current models being trained on only text. So I can maybe, before I continue with potential solutions, just check if there are any questions or thoughts at this stage that you would like to voice before I continue. Okay, I'm practicing this, not moving on too quickly after checking if there are questions. And I'm not sure if I succeeded, but feel free to interrupt me if you come up with anything you want to speak about. So now, if we assume that this is an issue, that language models are trained on only text, we can start to think about potential solutions to this problem. And of course, the most evident solution is to train models on more than text then, to sort of provide them with this additional information that maybe is lacking in text. And you can also interpret this as that we should create multimodal models. And with multimodal model, I mean a model that has been trained on several modalities. So text could be one modality, but images could also be another modality, or sound. So that is a multimodal model, a model that has been trained on, in this case, I interpret it as it has been trained on more than text. So for example, I could recommend an article, a survey, that sort of moves into this field of sort of investigating how can we sort of infuse text generation with knowledge in this case. So you can, for example, consider that everything is internal in the model, or you can consider the case that you have external knowledge, or you can see it as memory, because knowledge is maybe not necessarily always what you represent. So it could, for example, be that you have a knowledge graph or Wikipedia or some large text data set that you can just retrieve from. And in that sense, you can maybe incorporate the sort of additional knowledge that you can't get from only text and sort of use that with your model. And there are different methods that also are introduced in this article. And worth mentioning is that there was a model developed quite recently called Retro, and it was like 25 times smaller than models with comparable knowledge or with comparable performance. But the difference was that it was fused with a very large data set that it could sort of retrieve from. And then it became like very good and not having to be so large because it could sort of query some kind of external knowledge. And we also have, for example, this model called Lambda. So the Lambda part here is sort of a language model, but then you have like tool set that is an information retrieval system that incorporates an information retrieval system, but also a calculator and a translator. So then your language model can sort of query this tool set to sort of enhance its generations, which is quite cool. And this was for dialogue applications. And of course, you can also just take a model and train it on images as well as words. And that's something that quite a lot of research has been done on recently as well. For example, you have a model released by OpenAI called Clip, and that, for example, can reason about what you would see in an image. But we can also consider, apart from these potential solutions, it's also interesting to sort of consider, apart from this stochastic parrot reason, what other reasons are there for training models on more than text that maybe are more tangible and more evident that we have? So for example, and this argument may not maybe agree with everyone, but if we include more modalities, we maybe get a setup that is more similar to the learning process of a human. So of course a human can see, in the sense that it can view text, but it can also view images and different things. They can taste, hear, smell different things, touch, and sense things, but we can also interact with the world. So if I lift this heavy weight, if I put enough force under it, it will be lifted. And if I drop it on my foot, it will hurt. And if I move around it, I will see it from a different angle. And if I use a hammer on this glass, the glass will break. All those different kinds of things give us information that maybe isn't always present in text. So maybe having a model learn in a fashion that is more similar to this, we can maybe expect models to perform more in the same way as humans, because that can also be an issue, that we humans expect the models to act like us because they sort of talk like us. But if they haven't been trained in the same fashion, it's an interesting thought, at least. A more evident reason for training on more than text is that text actually suffers quite a lot from something called reporting bias. And I can illustrate this with an example. So here is an image of a straight banana. They are not common, but they do exist. Usually we see bananas that are curved, and that's usually what we assume when someone speaks about a banana, maybe. But if you, for example, Google for the word straight banana, you get about 180 million results. But if you Google for a curved banana, which is actually the most common form of a banana, you get only 12 million results. So you get about 15 more results on Google if you Google for straight bananas. And of course, that could be because straight banana maybe refers to something more than just the fruit in this case. But let's consider that we have a language model that has been trained on all of the internet, and which is something that Google can sort of query in. What that model would see is that the phrase straight banana occurs 15 times more than the phrase curved banana. And since it sort of models the probabilistic distributions behind words, it will assume that straight bananas are more common than curved bananas, while we know that is not the case. And the reason why we have this reporting bias is that we humans do not really report things that we believe to be common sense, or that we believe will not be of bring any extra information to the one we're speaking with. So, for example, I'm not telling you right now that I just took a breath, or that I'm sitting down, or that I have a spleen, because that's something you can assume that I do. Instead, I speak about things that I believe that you don't know about. And it's the same thing with text, that we write about things that are more uncommon. But if we have a model that only sees text, it will base its worldview on that. And that's an issue. We can also consider another reason for training on more than text is that we then get multiple views of the same concepts. So we can, for example, describe the concept of an elephant as saying that it has a trunk, a tail, large ears, 4 legs, and that it's gray, for example. We can also describe elephants with an image and just show an image of an elephant. But the thing here, for example, in text, maybe we forgot to mention that an elephant has eyes, because maybe that was evident to us and due to reporting bias. But if we look at the image, we don't see the tail. So in this sense, the text contains information about that an elephant has a tail, while the image doesn't contain that. On the other hand, the image contains information on that elephants have eyes, while the text does not. So we get like complementing views that might give us a better view of the full concept. And of course, we can take this even further. We also have the insides of an elephant. And we also know from sort of seeing elephants or getting an impression of their size we know that elephants are probably bigger than ants, which might not be easy to tell if you just get one picture of an elephant and you have another one picture of an ant. So those were some reasons for why training on more than text might be interesting in a more straightforward fashion. And we can also take a look at some of my research contributions within this area of having models learn from more than text. So one thing that I did together with Tobias and Rickard is to see whether we can measure some kind of visual conceptual knowledge in models. So for example, you saw the query about the color of a dove. Maybe we would expect a model that has seen doves to give a more correct answer on similar questions. So the thing we asked ourselves for this work was that, okay, let's assume that training on more than text should help. And let's assume that we're training also on images. What should it improve in the model? If we consider the first baby step the model can take in its sort of knowledge, what would that step be? So yeah, what would it improve in first? And we then thought about basic visual conceptual properties. So we created one data set called memory colors, which is essentially quite small, but it was based on querying human participants about the typical colors of different typical objects. And we used the word memory colors because that's actually a concept that is used, I think, within more psychology part, where it's actually shown that some things have memory colors in the sense that we remember them as having that color despite seeing them in another light or something like that. We also created a larger data set called visual property norms that queries for a bit more complicated features of visual concepts, such as about an elephant, what does it typically have, or what is it usually? And this data set was based also on human participants. They got to list in not our work, it's based on the concept property norms. But they asked participants to sort of list typical features of typical concepts. So then so both memory colors and visual property norms contains some kind of common sense knowledge of humans that they hopefully acquired from being able to see, or at least it encodes human knowledge, at least, of different typical visual concepts. And that's maybe something we would want the models to also acquire if they can sort of see. So yeah, so memory colors contain 109 objects that we queried for, and visual property norms contained about 6,500 features. And also worth mentioning is that we queried these models using text. So that's how we evaluated them. And we also tried with different queries because, as I mentioned before, the model may answer differently on how you query it. So what we found after evaluating a set of models, and this evaluation was based on visual property norms. I can start by mentioning that this x-axis production frequency essentially measures how common the feature was. So out of all the human participants, how many of them listed a feature. So the smaller the production frequency is, the maybe less common the feature was, and maybe the less plausible it is that a model should capture it. So we evaluated a set of multimodal models, that is models that have been trained on both text and images, and these are the ones I marked in black. And the rest are models that were trained on only text. So here we see the maybe best performing model, which is a multimodal model called Clipbird. So it's based on the clip model I showed also previously, and on BERT. And here we have the second best result, and that's actually from a unimodal model. So that is a pure text model. And we can see how, I mean, of course, it's hard to reason about performance differences with large standard deviations, but it's not evident that the multimodal model that has seen images performs significantly better at this task. And of course, it can be due to several reasons, but seemingly from our results, it doesn't really help yet with, or at least with our hypothesis in what the models should improve in from training on more than text, training on images. well, we couldn't confirm that hypothesis. And actually, similar results have been seen in different articles. I have missed to link them, but feel free to ask me. But so far, it seems as though our current models, we have somewhere we fail in sort of fusing this knowledge. So the models do not become better than pure text models on things that we expect them to become better at when training on images. Another thing I've also been working on quite recently, quite a small project, but it's essentially sort of considering this setup. So if you have a model that you want to train in both text and something else, and typically that something else is images currently, you have your image, and then you have an image model that takes in your image and creates a representation of it. And then you feed that representation and some type of text, maybe a query of what's in the image into your language model. And then you maybe get an answer from your model. Maybe it shouldn't be referred to as a language model because it's multimodal. But then you get some kind of answer maybe. And this is the typical setup for multimodal models. But the problem with this is that fusing information in this way typically entails some difficulties. So for example, it has been observed that these image features or this representation that we get from an image model can be quite noisy. So typically you use object detectors, and it can be very different in what the object detector detected, and it can be very noisy, which sort of doesn't help the language model. And also generally since you're using images and also a very large image model, it also entails larger compute demands and storage. And also the setups become a bit difficult to debug, because where does the issue lie in if the model doesn't perform as you would hope from training on images? Is it something wrong with the image model, or with your input data, or with how you fuse the information from the image and from the text? And so our thought was, can we somehow more efficiently discover promising methods for fusing language models with additional information? So sort of try to simplify this setup just to get some kind of prototyping version of it. And the idea was to sort of, what if we replace images with arithmetics for fun's sake? And here we get an additional information input that is maybe a bit less complex. You still can have different values over sort of different pixels, but they have a much more limited domain that they cover. And you can also more easily artificially create them, while they still have a structure, because it needs to sum up correctly on the left side and the right hand side. And so that's also something I've investigated recently. And we found that you can essentially reproduce similar behaviors in the with the math model setup as in the image model setup. So maybe you could experiment with like sandboxed versions of multimodal fusion at this stage, and then transfer them to the more complicated stage. Was the idea, at least. So that was a bit about my work, and I see we have 20 minutes left approximately. So I can just quickly go through some research ideas that also might be interesting to pursue within this area of training on more than text. And one thing that could be interesting is to consider the more causal structure, or a more sort of causal approach to this, which essentially entails that you try to sort of put in some kind of assumptions on your setup. So in this case, maybe what we really want to do is to extract intent from different queries. So let's say that we have these 3 different queries essentially ask for the same thing, so they have essentially the same intent. Could we sort of extract that somehow instead, and then use that for our answer? So we maybe query some kind of memory and then answer, and then we are sort of robust in how we answer to different queries. And then this sort of maybe causal approach comes in here, in that we actually assume that there is some kind of intent that needs to be extracted before, and in how the structure should be. And also one interesting approach is to use knowledge graphs to explain language models. So let's say that you have a language model that you have sort of connected with some kind of knowledge graph, and that graph, for example, contains information about what the color of a dove is, that it is gray, and then you can expect the model to sort of follow this knowledge in its generations. Of course, it's probably not as simple as this, but the idea is still interesting to investigate if this is possible. And one last thing still that's interesting to consider and also discuss, that I believe is maybe one issue within this field of training on more than text. And it can sort of be visualized firstly through a set of examples. So what you see here is a user querying a model called Gopher. So Gopher is a language model that is quite large and recently developed. And you see here how the model can answer different questions about black holes and metrics and differently. But then it's queried on what is 15 times 7, and then it answers 5, which doesn't seem as cool anymore. There are also some quite old examples, but still maybe reasonable in this context of, for example, how you can just add some kind of noise on top of an image of a panda, and suddenly your image recognition model says that what you see is actually a given, while we can't see any difference between the images. Another issue that has been raised is that, for example, if you have a model that should recognize entities in an image, and you switch the background of the entities from what they typically are. So in this case, you have cows usually on green pastures, but suddenly if you show the model an image of a cow on a beach, the model will no longer recognize that there is a cow in the image, because cows shouldn't be on beaches. So if we, for example, consider some kind of scale where we on one side have complete gibberish in understanding, and we on the other side we have human-like understanding, it maybe appears as though, for example, our current language models are quite close to human-like understanding in many cases, and they reach quite far, and they can do quite a lot of cool stuff and be queried in different cool ways. And then maybe if we try to introduce some kind of multimodal model, it will seem less cool because it maybe doesn't achieve as well within the different areas that we investigate. The problem, however, might be that essentially your language model is maybe not as good as you would expect, in the sense that it maybe sort of overperforms in that it can come quite a long way on using probabilistic measures. And this can of course be an issue, because maybe it's not as cool to try to take steps back and use quite simple examples. And of course, maybe we could also have the same case with image processing systems, although I should mention that I'm not very well versed in image processing systems, so take all of the things I say about that with a grain of salt. So this maybe prompts an interesting question, that is sort of what problems can we apply our models to? I believe that there are application examples, but maybe not always what we maybe would hope. So this is actually my last slide. Maybe I don't know if I ended on quite a sad note, but what are your thoughts? Do you agree? Do you disagree? Do you have any ideas on how you would like to fix this problem, or do you have any applications that you think would be interesting for this? So yeah, that's it for me. I can just show you quickly. Thank you for listening, and then see if you have any questions.
Yes, I have a question.
Yeah.
Hello, Lovisa. Thanks for a nice presentation. My name is Magnus Holgren. I'm one of the authors of the Singleton Fallacy paper.
Yeah. yeah.
Yeah.
I hope I did your paper justice.
Yeah. No, but obviously, I don't agree with the Bender and Collar arguments. And I would be curious to learn a little bit more about your actual thoughts of this. So you were referring to the idea then that intents are somehow outside of language, but they should also be represented in language, right? Because otherwise, how can we communicate intents? So if we only observe the linguistic signal, we should at least be able to detect the symptoms of intents, right? And then we should be able to learn about intents and also communicate them by only observing the linguistic signal. So I'm just curious to know if you really think that intents are unobtainable from language. So that's a more philosophical question. but I think there is maybe a more practical one also here. I think there are two sort of conflicting arguments here, really. So one is about text being the only medium that we learn from. And of course, text is not only one simple thing. It can be instructive text, and it can be also meta text, so text about text, etc. But so you have the medium, and you have the potential to not be able to learn all the sufficient information from this medium alone. But then you also have the other argument, which is, okay, so we're now using distributional learning criteria on this medium. Is it the text medium, or is it the learning criterion that is not sufficient to learn all the information that you would like to get at? Okay, so two sort of fluffy philosophical questions.
Yeah, but very interesting and very fun and very nice that you listened to my presentation.
It was a great presentation, by the way. Yeah.
And thank you. Yeah, and great questions. So as for, I can maybe start with your last question, where I think what you asked for is sort of, is the thing that's lacking the sort of data source, the text in this case, or is it actually what we sort of use as objectives when we train on text?
Yeah.
I would say, let's see here. I would say it's maybe both, because I actually haven't considered this so far, but I would say that, I mean, obviously we have our models now that get very good results on, for example, superglue and glue. But evidently in other regards, the models don't perform the way we would hope them to in certain cases. So of course, then that means that our sort of objectives aren't good enough, because we don't cover what we thought we covered. I know also there are examples of other benchmarks. For example, there is a data set checking for common sense reasoning called SWAG. And what was found was that there was bias in the sort of queries in this data set. So the model could answer most questions correctly without even knowing what the question was. So then that means that, of course, our objectives somehow don't cover what we should cover. But again, as for the text, I would also say that, of course, you can sort of condition text such that it contains the information that you're looking for. But that's probably not text that we create naturally, because we use other modalities to complement our text. So as in the sense with reporting bias, we probably will not speak too much about curved bananas, because you can see that from walking into a grocery store. And of course, you could create your own text that sort of reinforces that curved bananas are more frequent. One thing, for example, we did in our experiments was to train a language model on sort of captions. So we just take the text part of an image text data set. And then we found that that model could become better at sort of queries about visual knowledge, because it was trained on text that maybe actually did say that bananas are yellow. So of course you can cover it in that sense, but I think if we just scrape down information from the internet, we will probably get a distribution that assumes that you can see other things than just text, and then maybe you will miss things. So I think that's maybe my answer to your second question, if it makes sense.
Yeah.
And then let's see here, you had your first question.
Yeah, do you really believe that there are things that are unobtainable from the linguistic signal?
I mean, it depends on how you interpret it. As I said, you can, of course, condition your text to contain that information. And in the same sense, you can do with the training that if you just get enough text, the model can sort of achieve comparable knowledge. But I still think it's interesting to, I mean, still consider it to be a problem, such that you can look at other alternatives than training on text, just for the sake of it. Because, as I said, the information could be there, but maybe it won't be as efficient to get it from that source. Maybe it could be more efficient to get it from the multimodal sources. So that's maybe one thing, more like sample efficiency. So I think,
Yeah, I think you're completely right. I would agree to the poverty of the stimulus argument, so that text might be too sparse of a signal to learn more efficiently from. But I am quite hesitant to the critique that Bender and Collar raises, that text is sort of insufficient to learn intents. I don't believe that.
Yeah, I understand. Yeah, I understand that. I think I like to agree with them because I think it's fun to get some kind of probing on sort of, let's assume that this is correct, and then we can start to do interesting things with it. But yeah, and they are very good at framing their examples.
Yeah.
So yeah.
Thanks, Lovisa. Nice presentation.
Great. Thank you.
Thank you, Lovisa. So sort of given that you want to ground your model in something, what would you say would be the sort of the optimal source for the grounding? Is there such a thing, and can we, in such case, can we find what would be the best source for the grounding? I mean, images has its limitations, I suppose.
Exactly. Yeah, and I think that's a very interesting question. And I think it also sort of depends on what do you want to use the model for, because we can use language in several regards. Currently, the thing I am most interested in is actually knowledge graphs. I haven't worked that much with it yet, but essentially something that contains some kind of structural description of knowledge. Because what's nice with that is that you then get some kind of visibility into what the model will base its predictions on. And also you can sort of incorporate, I don't know, different types of knowledge. Of course, then there is the issue of obtaining that graph and having it contain the correct knowledge. But I think it's an interesting place to start. But of course, it depends on what you want to use it for. And of course, I suppose it would be best if you could use any possible modality with regard to this like multiple use idea. But yeah, but those are maybe my opinions. Do you have any thoughts? What would you like to ground your language model in?
I don't really know. I don't really know. I suppose all kinds of data sources have their limitations, and I suppose also what sort of is also sort of what is the goal of the grounding? Is the goal that we want? I mean, you mentioned in your talk, if we want the model to do the same thing as the human do, is that the goal, or is the goal that we want sort of the model to learn what the brain knows about stuff or about language? I don't know.
Yeah, that's also a very good question that I maybe didn't cover well enough. But yeah, that's really true. It's very hard to measure. How do we know that it does what it wants us to do, and what's the definition of good performance? That's really hard.
So a question. Has there been any trials on extracting information from video, having like vision models, and I mean any modalities basically, because language is, as I see it, some kind of abstraction of understanding of the world, and that is the problem, because we try to understand the output and relate that to our own understanding of the world. And if you would give it like a multimodal input, like sound, video, whatever, how far have people come in that regard?
There has been quite a lot of work on that, on incorporating language with video and with audio. I haven't looked that much at it myself, but I know that there is work on it, and I also have actually Sam, the one who's also part of my project group. He actually has worked a bit with fusing videos with language. And so I could look that up and see if he has any like article recommendations. But yeah, there is work on it. Although I think still one problem also within that field is that you need to be able to have something that extracts the information that you want from the video, and sort of gives that information to your language model. And even already in images, we can see that that it sort of doesn't, the models aren't good at extracting that information from the images. So while the information might be there in the video, how do you extract it in a form that makes sense to language model? But yeah, there is work on that.
Right. Right. Okay, thank you.
I can also add, feel free to email me if you have any further questions or can't ask them here. I'm very happy to discuss this further.
Great. Then we'll thank the speaker. I'll just add that next week we'll have another speaker, Martin Trimell, who is a PhD candidate in Lund University, is going to talk about linear regions of deep neural networks. The week after that, on April 7th, we have another talk on the topic of natural language processing with Professor Kyung-Hyun Cho at New York University. He's going to talk about characterizing and addressing the issue of oversmoothing in neural autoregressive sequence modeling. I would think that this connects a little bit to some of the things that you mentioned today, but more from sort of the robustness side of the language models. Sort of when the model does something that we think is sort of wrong, why is it doing this? And I think this talk is going to be more on sort of the objective side of that and less on the grounding side. But thank you for a great talk today. And thank you also for all the questions and discussions here.
Thank you. And thank you for letting me come. Bye.
Bye-bye.